The Cascadia megaquake will likely be the biggest disaster to
Could a monster earthquake sink a portion of Northern California?
The ground beneath the Pacific Northwest has been sending signals that are impossible for scientists to ignore. Deep beneath the coastal waters where the North American and Juan de Fuca tectonic plates meet, a colossal geologic structure known as the Cascadia Subduction Zone has entered a phase of unusual restlessness. Instruments scattered across the region have been recording a surge in seismic and geophysical activity, the kind of changes that prompt geologists to switch from quiet monitoring to urgent warnings. Now, with patterns escalating and key indicators aligning in unsettling ways, the official classification has shifted to a red alert. Before we start, smash the like and subscribe buttons for more updates. This subduction zone is one of Earth's most formidable geological features, stretching roughly 620 miles from Northern California through Oregon and Washington and into British Columbia. At its core, it is a slow-motion collision between two immense slabs of the planet's crust. The smaller, denser Juan de Fuca plate is sliding beneath the North American plate, being consumed into the mantle at a rate of just a few inches per year. While that might sound gentle, the forces at play are anything but. Over centuries, the plates lock together, storing vast amounts of stress until the bond snaps, releasing the pent-up energy in the form of catastrophic earthquakes. For decades, the Cascadia Subduction Zone has been quiet compared to other plate boundaries, a deceptive calm that many geologists have compared to a loaded spring held in place by an almost imperceptible catch. Historically, this region has produced some of the most powerful earthquakes and tsunamis on record, though its most recent major rupture occurred in 1700. That event sent shockwaves across the Pacific and triggered a tsunami that struck the shores of Japan. Since then, the absence of a similar rupture has not been a sign of safety. It has been a silent warning that the region is still building toward another massive release of energy. Recent months have seen a marked change in the behavior of the subduction zone. Seafloor pressure sensors have begun detecting subtle but accelerating shifts in the deformation of the ocean floor. This is not the slow and steady creep typically observed in a locked subduction zone. Instead, it is a series of uneven surges, movements that suggest sections of the boundary are straining in new ways. Offshore GPS stations are showing millimeter-scale adjustments that, when taken in isolation, might seem insignificant. Yet when those readings are mapped and compared over time, they form a pattern consistent with growing instability deep within the fault zone. Seismographs across the Pacific Northwest have been lighting up with tremors, some too small for people to feel, others large enough to be noticed by residents along the coast. Many of these events are classified as low-frequency earthquakes, a type of seismic signal associated with the slow slip of rock deep underground. These slow slips can release stress in a gradual fashion, but they can also redistribute it toward more dangerous, locked sections of the fault, increasing the risk of a major rupture. The current wave of such events is more frequent and more intense than usual, a sign that the subduction system is shifting into a more active state. Beneath the seabed, hydrothermal vents have shown subtle changes in temperature and flow rate, suggesting that fluid pressures within the fault zone are fluctuating. These fluids, often heated and driven upward by the immense tectonic forces, can play a critical role in how stress is stored and released. An increase in pore pressure along a fault can reduce the friction holding it together, potentially pushing it closer to failure. Taken together, these indicators, accelerated slow slips, shifting seafloor, and changing fluid pressures, paint a picture that has geologists deeply concerned. The decision to declare a red alert is not taken lightly. Such a designation means that the probability of significant seismic activity has risen sharply compared to background levels. It does not mean a massive earthquake is guaranteed to strike within hours or days, but it does signify that the conditions for such an event are more favorable than they have been in years. For scientists who study the Cascadia Subduction Zone, this is the moment when observation shifts into heightened vigilance, when every signal is scrutinized for signs that the system is approaching a tipping point. One of the most striking elements of the current activity is how widespread it appears to be. Rather than being confined to a single locked segment of the fault, the changes are occurring along a broad stretch of the subduction interface. From the southern reaches near Cape Mendocino up through the rugged coasts of Oregon and Washington, instruments are detecting coordinated shifts. This kind of synchronized behavior suggests that the stresses in the fault are interconnected, meaning that movement in one area could easily influence conditions hundreds of miles away. Geologists have long known that the Cascadia Subduction Zone is capable of producing magnitude 9.0 earthquakes, events so large they can shake the entire Pacific Northwest for several minutes. These megaquakes are accompanied by massive tsunamis that can strike the coast within minutes of the initial rupture. While the red alert does not claim that such a scenario is imminent, the patterns emerging in recent weeks are uncomfortably similar to models of the buildup phase preceding a large-scale rupture. The importance of monitoring extends beyond earthquake prediction. Understanding the Cascadia Subduction Zone's behavior is also critical for mapping out which areas are most at risk from secondary hazards. The seafloor deformation being recorded now could help scientists refine their tsunami models, showing how and where the ocean floor might rise or fall during a major slip. The ongoing changes in fluid pressure could help explain which portions of the fault are most likely to fail first, and which might follow in a cascading sequence. Part of what makes the current surge in activity so concerning is that the Cascadia system does not have the frequent moderate earthquakes that characterize places like California's San Andreas Fault. Those smaller events often serve to release some of the built-up energy before it reaches catastrophic levels. In contrast, the subduction zone tends to remain locked for centuries, only to fail in a single massive rupture. This pattern means that unusual signals, like the ones now being detected, are taken especially seriously. Research vessels have been dispatched to key offshore locations to collect more precise data from ocean bottom seismometers and pressure sensors. These ships are also retrieving sediment cores that can reveal past earthquake and tsunami activity, offering clues about the frequency and scale of prior events. Each core contains a layered history of disasters, recording the times when the seafloor suddenly shifted and sent walls of water rushing toward the shore. Scientists compare these layers to modern data, looking for patterns that might reveal where the current cycle stands in relation to previous ones. Satellite-based radar interferometry is another tool now being used extensively to track minute changes in the shape of the land. By measuring ground displacement to within a fraction of an inch, these satellites can map the slow warping of the Earth's surface as tectonic forces accumulate. In the past few weeks, imagery has confirmed subtle but significant uplift in some coastal areas, along with sinking in others, classic signs of strain redistribution within a subduction zone. The collaboration between geologists, seismologists, oceanographers, and emergency planners has intensified. Data is being shared in near real time, allowing for rapid analysis of any anomalies. While the red alert is a scientific classification rather than a public evacuation order, it serves as a crucial signal to coastal communities, infrastructure managers, and decision makers that the tectonic system is behaving in ways that could precede a major shift. To understand why the Cascadia Subduction Zone demands this level of attention, one must consider its potential reach. A full margin rupture would not only affect the immediate coastal region, but could also disrupt systems far inland. Cities such as Portland, Seattle, and Vancouver sit within range of intense shaking. Critical supply lines, energy grids, and communication networks cross areas that could be severely damaged. The potential for landslides, soil liquefaction, and aftershocks adds further complexity to the risk profile. The surge in seismicity and deformation is also a reminder of the intricate link between Earth's deep processes and the environment on the surface. Coastal ecosystems depend on the balance between tectonic uplift and subsidence. Sudden changes in that balance can reshape estuaries, alter river courses, and shift habitats. For scientists studying long-term climate and ecological patterns, the current activity offers a rare opportunity to observe how large-scale geologic forces interact with the biosphere in real time. Some of the most important work happening right now involves modeling the fault's behavior under different stress conditions. By feeding the latest observational data into computer simulations, researchers can explore how the system might respond to further strain. These models can test scenarios ranging from continued slow slip to partial ruptures or full margin breakage. While no model can predict the exact timing of an earthquake, they can help refine the range of possibilities and improve the readiness of both scientists and the public. Another point of focus is the role of deep tremor and slow slip events in triggering or delaying larger earthquakes. The current wave of low-frequency seismicity could be transferring stress toward shallower, locked segments of the fault. Alternatively, it could be relieving just enough pressure to postpone a major rupture. Determining which of these outcomes is more likely is a complex challenge, one that requires constant comparison between present signals and historical precedents. The red alert underscores the importance of the dense network of sensors that now blankets the Pacific Northwest, both on land and at sea. Many of these instruments were installed over the past 2 decades precisely to catch early signs of unusual behavior in the Cascadia system. The fact that they are now recording such a coordinated surge in activity is both a validation of that investment and a call to action for researchers to interpret the signals accurately. While the public often associates seismic alerts with imminent disaster, in the scientific community, a red alert is more akin to a weather forecast warning of a powerful storm system forming offshore. The conditions are present, the energy is building, and while the exact path and timing remain uncertain, the potential impact is too great to ignore. This is the phase where preparation and observation take precedence, where every new piece of data could tilt the understanding of what comes next. In the case of the Cascadia Subduction Zone, the implications of the current activity reach beyond seismic science. They touch on coastal planning, marine safety, and even international coordination. Tsunamis generated by a rupture here would not respect national boundaries. Their waves would traverse the Pacific, affecting countries thousands of miles away. That reality makes the present surge in activity not just a regional concern, but a matter of global interest for geoscientists and disaster readiness agencies alike. Even without an immediate quake, the forces at play beneath the Cascadia Subduction Zone are a reminder of the dynamic nature of the planet. The ground may seem solid and immovable underfoot, but it is in constant motion on a scale that human senses cannot perceive without instruments. The red alert serves as a visible sign of that hidden motion, a translation of deep Earth processes into a language that can guide human awareness and action. As researchers continue to watch the fault, the emphasis remains on collecting and analyzing every available signal. The more precisely the current surge can be characterized, the better the understanding of the subduction system will be when the next major rupture does occur, whether that is soon or decades away. In the meantime, the ongoing activity is offering a rare glimpse into the inner workings of one of Earth's most powerful geological engines, a reminder that even in its quietest moments, the Cascadia Subduction Zone is never truly at rest. Far below the restless waters of the Pacific, the Cascadia Subduction Zone has a history written in rock and sediment that stretches back millions of years. To understand the significance of its present surge in activity, it helps to trace how this immense fault came to be and why its mechanics make it one of the most dangerous geological systems on Earth. The subduction process here began when an ancient oceanic plate, the Farallon Plate, fragmented and disappeared beneath the edge of the North American continent. The small Juan de Fuca Plate is a remnant of that much larger slab, still sliding eastward into the mantle. Unlike faults where two plates grind past one another horizontally, a subduction zone pushes one plate downward under another, creating a massive interface that dips deep into the Earth. This sloping plain, stretching from the seafloor to hundreds of miles inland, is the surface along which strain builds. At shallow depths, the rocks in contact along this interface are cold and brittle, locking together like the teeth of a gigantic zipper. Deeper down, heat and pressure make them more ductile, capable of creeping slowly under stress. Between these two zones lies a transitional region where seismic events can begin and then either fizzle out or cascade upward into catastrophic ruptures. The Cascadia Subduction Zone is remarkable for the length of its locked section, which may extend for hundreds of miles offshore, long enough to unleash a single continuous rupture along most or all of the boundary when it finally fails. Over thousands of years, the region has experienced cycles of quiescence followed by violent release. These cycles have been reconstructed by examining coastal marshes, river deltas, and offshore sediment layers. When a megaquake strikes, entire swaths of coastline drop abruptly by several feet, drowning forests and turning low-lying areas into tidal flats. In the centuries that follow, these subsided areas slowly rise again until the next rupture resets the landscape. Core samples from ancient peat and sand layers, as well as drowned tree stumps preserved in tidal mud, reveal a repeating pattern of such events stretching back at least 10,000 years. While the long gaps between large earthquakes might seem reassuring, they are deceptive. The absence of recent massive shaking is the result of the plates being firmly locked, a condition that allows strain to accumulate to extraordinary levels. In effect, the longer the locked section remains immobile, the more potential energy is stored. The current surge in activity is troubling precisely because it suggests the system's balance may be shifting, potentially moving from its centuries-long buildup toward release. Part of what makes this alert unique is the diversity of signals being recorded. Geophysical instruments are detecting not only the subtle slips and tremors deep beneath the surface, but also changes in magnetic fields along the fault zone. These magnetic variations can occur when stress deforms rock containing magnetized minerals, slightly reorienting their alignment. In some cases, shifts in magnetic readings have preceded significant seismic events, though the connection is still an area of active research. The current changes are small but measurable, and they match the geographic spread of other anomalies now being monitored. Acoustic monitoring from ocean bottom hydrophones has added another layer to the picture. These devices, originally designed to study marine mammals and submarine landslides, are now picking up faint, low-frequency rumblings that appear to originate along the fault interface. The tones are too deep for human ears, but stand out clearly in spectrograms. Scientists suspect these sounds could be generated by fluids moving under high pressure through fractures, or by the grinding of rock surfaces as stress redistributes. Either way, their growing prevalence fits the broader pattern of heightened geologic unrest. What is happening offshore is also influencing the onshore environment in subtle ways. Certain hot springs along the Washington and Oregon coasts have exhibited slight temperature and flow fluctuations, likely tied to changes in the deep plumbing systems that connect to fault zones. Although these changes are small, they are consistent with the idea that fluid movement at depth is playing a role in the current instability. Some monitoring wells have even detected tiny shifts in groundwater chemistry, such as increased silica content, which can indicate that water is interacting with freshly fractured rock. The ability to track these minute changes is a testament to how far monitoring technology has come since the last Cascadia rupture in 1700. Today, the region is part of a massive sensor array that includes seafloor cables capable of relaying data in real time. Some of these systems are tied into the Pacific-wide Deep Ocean Assessment and Reporting of Tsunami's DART network, which uses anchored buoys to detect tsunami waves as they travel. These same buoys can also register pressure changes from seafloor uplift or subsidence, movements that are now showing distinct anomalies in several sectors of the subduction zone. Geologists analyzing this data are particularly concerned about the possibility of segment coupling changes. The subduction zone is divided into several overlapping segments, each with its own degree of locking and stress accumulation. When one segment begins to slip, it can either stop at the boundaries of neighboring segments or trigger a chain reaction. Historical and geological evidence shows that Cascadia is capable of both partial and full ruptures, but the synchronized nature of the current anomalies across multiple segments hints at the potential for a broader scale event. The offshore topography compounds the hazard. Along parts of the subduction zone, steep underwater slopes are draped with thick layers of sediment carried down from rivers over millennia. If a major earthquake shakes these slopes, vast quantities of sediment could collapse in submarine landslides, adding to the tsunami hazard. Such slides can create waves independently of tectonic uplift, and in some cases they can amplify tsunami heights in localized areas. The recent seafloor pressure changes raise questions about whether some slopes might already be closer to failure. The red alert has also intensified interest in the subduction zone's relationship with volcanic activity in the Cascade Range. While the volcanoes themselves are driven by magma generated as the subducted plate melts deep underground, changes in the stress regime of the fault can influence the pathways that magma takes toward the surface. In the past, some slow slip events have coincided with minor increases in volcanic seismicity. In recent weeks, a few volcano monitoring stations have detected small bursts of tremor unrelated to magma movement, possibly reflecting stress transfer from the offshore fault. These findings are still preliminary, but they are being watched closely given the complex connections between tectonics and volcanism. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the Cascadia Red Alert? What do you expect will happen? We want to hear from you. Thank you for watching, and see you next time.